SwayamPrabha. Digital India. Educated India.
Welcome to the DTH sponsored course on micromachining. In the last lecture, we discussed about the electric discharge micromachining EDMM. Now this lecture also continues further with the electric discharge micromachining, that is the part 2. What we have done in the last lecture are following: introduction and working principle of EDM and EDMM, where I have told you how the material is removed from the workpiece, that is by melting and vaporization. What kind of heat source is considered when we are conducting the simulation or theoretical analysis. Normally it is the Gaussian heat source which is being considered, although some researchers have also used uniformly distributed heat source or some point heat source also. Comparison of EDM and EDMM also has been presented, where various parameters, specifically the machining parameters, what machining parameters values are taken in EDM and what machining parameters values are taken in EDMM are discussed, just like voltage, pulse on time, pulse off time, duty ratio, current density and inter-electrode gap. EDMM machine setup have been shown. Now here I have shown some of the setups developed at IIT Kanpur and some of the manufacturers who are supplying the electric discharge micromachining setups from different countries, especially Singapore, Germany, USA and other countries. Process parameters and micro tools fabrication, very important aspect. There are various process parameters like current, voltage, on time, off time of the pulses, type of the pulses, different types of the pulses may be used, and then tool material properties as well as workpiece material properties, they affect the performance of the EDMM as well as EDM process. Then very important aspect, that is the micro tool fabrication. When we are talking of electric discharge micromachining, we are using micro tools for machining purposes, and how to fabricate those micro tools. So I had discussed with you about the fixed block, rotating disc, rotating wire, EDM or ECM processes that are used for fabrication of micro tools. Normally conventional methods do not work satisfactorily for fabricating micro tools, especially few tens of micrometer. Then we also discussed types of EDMM operations, where we discussed electric discharge micro drilling, electric discharge milling, electric discharge micro turning and so on, and what are the different types of the motions given to the tool and workpiece during these operations are also discussed in the last lecture. Now let us discuss the specific applications of electric discharge micromachining process. Applications of EDMM: small precision cutting punches and dies, precision molds, components for medical engineering, very important applications, sensors and optics, definitely in micron size, watchmaking, gears and holes, and small multi-component electrodes These are some of the important applications of EDMM process. Microsensors with 0.051 millimeter, that is 51 micron slots, and extrusion matrix with 0.25 millimeter slots. They are shown over here, as you can see. This is the one with the microsensor, and this is the one with extrusion matrix of 250 micron slot. They are shown over here, and this sensor is over here. Now here you can see other component. Micro gear is fabricated over here, that's shown. Its dimensions are 600 micrometer, which is quite small, that is 0.6 millimeter, and depth here 100 micrometer, and this is the another component shown from which this has been, on this one it has been made. This is the enlarged view of that micro gear, and you can see here this is from this particular reference. Electric discharge micro milling applications, as you can see here, these are the micro milling component where micro milling is being done. 100 micrometer is the scale. So ED micro milling tools of tungsten carbide are being made over here. Diameter is 100 micrometer. Now here you can see and this is the closed view of electric discharge micro milling process and finished turbine impeller. Here see it can, this is the indexing clamp, and this is the micro milling being performed. This is the tool, and micro milling is performed over here. Now you can see here tungsten carbide electrode is there, again micro electrode is there, and this is ceramic blank on which milling operation is being performed. You can clearly see this is the turbine impeller which is being machined over here in the micron sizes, and this is the hub surface which has been milled, and this is the suction surface. This is this one blade suction surface, this is the hub surface, and this is the pressure surface. They are being milled by electric discharge micro milling operations. So you can see you can perform micro milling on very hard material and for very important components like turbine impeller. Further applications of electric discharge micro machining, you can see here this is the 6.5 micron size hole has been drilled on 50 micron size stainless steel blade, and this is the minimum one which has been drilled, and this is the maximum 12.5 micron size hole. That so a series of holes have been drilled using electric discharge micro milling operation. Now this is another example, 2.5 micron wall separating and 12 micron slot. This is the 12 micron and this is a 2.5 micron size wall separating these two slots, and all this is done by electric discharge micro machining. This is the another important component, micro turbine in steel, and you can see here this is the turbine which has different components like bearing, turbine rotor, and stationary nozzles are there, and this is the scale you can see here. So different micro milling operations have been performed to make this micro turbine, and you can compare the sizes. This is the matchstick. So what is the size of this matchstick here? You can compare with this, and this is the larger size. Microfluidic channels in stainless steel, you can see here different sizes. All these are in microns because this scale is 100 micrometer. Now this is another example of smallest electrode, that is 2.54 micron size. This is the smallest electrode that has been fabricated, and you can see this is the human hair. So this is much smaller than the thickness of the human hair. This is the thickness of the human hair, and this is the electrode 2.54 micron. Now you can see the micro holes are drilled in this cylindrical component, that is the material is platinum, which is very hard to machine. This is the micro gear which has been fabricated with the help of electric discharge micromachining. Dimensions are not given here, but all those dimensions are in micrometers. Now, electric discharge milling of channel, and this work was performed at IIT Kanpur. You can see here material removal phenomena. This is rotating in this direction, and this is the material being removed. Fluid flow direction is there, because dielectric is the fluid, and this is flowing. You can see over here milling marks are there, and this is the thermal process. So, definitely you can see here the craters, small size craters that are also visible. So, SEM picture showing the swirling action, this is the swirling action, and the milling marks are there along with the craters. These marks are generated during machining due to rotation and forward feeding of the tool, which is used for milling purposes over here. Machined micro channels, you can see here, this is one micro channel which has been machined, and this is the another one, blind one. So, SEM picture showing side view and top view of the different micro channels. This is the top view and this is the front view or side view. The uniformity of the taper is seen on the side and at the edges. Now, another example, this is the 50 micrometer electrode end view. These are the 5 electrodes which are used, 68 micron wide slot, these are the slots. 50 micrometer electrode is there, which is used for making the slots over here. As you can see here, 68 micron slots are there using these tools. So, you can simultaneously make 5 slots at the same time. And here is another example of 6 micron diameter electrode. This here it is 6 micron and it is stepped electrode where diameter is continuously increasing, and this has been used to drill the hole over here. 22 micron size hole has been drilled over here using this 6 micron size electrode. Now, what you can think here is, or you can examine here carefully, is that electrode diameter is 6 micron while the hole drilled is 22 micron. So, there is a lot of overcut in this particular process. So, definitely it also indicates that the process was very slow. So, lot of material has been removed from the workpiece. Now, here also overcut you can examine, it is the 68 millimeter, 68 micrometer wide slot with the help of 50 micrometer electrode. So, definitely 18 micrometer overcut was there in this particular case, diametral overcut. So, the radial overcut will be half of it if both it is uniform on both the sides. So, ED drilling using solid electrodes over here. Now, this is very interesting example. This is a micro mixer which has been machined with the help of electric discharge micro machining process. Now, microfluidics mixer is there and you can enlarge this part. This part is like this. Now, you can see how many very small parts are there over here, here, and when the fluid is entering into this and going out, then it gets very well mixed up, and that is what is known as microfluidic mixer. So, such kind of the devices are fabricated with the help of electric discharge micro machining process. Here you can see 520 micron diameter extrusion die. So, this particular die can be used for making micro components of micron size. This is a extrusion die, you extrude through this and you will get the extruded micro components. This is the ladder with 100 micron gap between the teeth. These are the teeth, 1 teeth, 2 teeth, 3 teeth, and this is the 100 micron gap between the 2 teeth. Then you have this 655 micron size pin over molding jig, 655 micron size holes are there, these two, and then you have the micro gear, 52 micron diameter, which is very small. This diameter of this is 52 micrometers. So, you can imagine the sizes of these teeth of the micro gear. And This is the another which is still a smaller gear made by electric discharge micromachining process. So, you can see you can make complicated devices of micron size using this particular process. Now, let us see little bit theory involved in the EDM and EDMM process. So, let us see analysis of the EDMM process. Empirical modeling of EDMM. You know, you can do the modeling of any process which may be theoretical modeling, it may be numerical modeling, it may be empirical modeling. Empirical modeling is performed using the experimental data or experimental information, and please note it very carefully. This is valid only for the used tool material, used workpiece material, used dielectric and used machining conditions. If any of these varies or changes, then these modeling will not give you the satisfactory results. Influence of pulse characteristics, parameters determining the energy of micro EDM pulse plays an important role, and this energy is given by E is equal to VIT, where V is the voltage, I is the current in amperes, and T is the pulse time in seconds. If it is very small, it can be in microseconds also. For energy pulse with on and off times, this equation can be modified to E is equal to Vp Ip multiplied by T on over T on plus T off, right, where Vp and Ip are voltage and current of a single pulse respectively, and T on and T off are pulse on time and pulse off time respectively. So, in case of pulse power supply, this is used; in case of direct power supply, this is used. But in most of the cases, we are using a pulse power supply, and it is the pulse power supply which is used in EDM as well as EDMM process. So, MRR can be given using this particular equation: Vp Ip T on multiplied by T on over T on plus T off, where alpha is material removal constant of individual material, and this alpha is to be determined with the help of the experimental results, and sufficient number of experiments should be performed to accurately determine it. Otherwise, this will not give the right values of material removal rate or volume of material removed. Let us see influence of tool and work related parameters. There is electrode wear during EDM and EDMM, especially at low material removal rate, which greatly affects the finish and accuracy of the process, and these both of them are very important for the finished component. Electrode wear resistance index, this is very important, and not much work has been done in this particular direction. So, people can do lot of research activities in this establishing the wear resistance indices for different types of the electrodes or different materials of the electrode, especially the tool material electrode, is equal to rho C lambda T MC multiplied by T V C, where rho is the density, C is the specific heat, lambda is thermal conductivity, T MC and T V C are melting and boiling point of tool material respectively. As I have just mentioned, this is very important, and this will help a lot in the tool design for EDM processes and EDMM processes theoretically, because that is very much needed if you want accurate component to be machined in first go itself by these processes. mathematical modeling of EDMM. Earlier one was the empirical modeling. Let us see how people have attempted to develop a mathematical model for electric discharge micromachining process. Some aspects of modeling needed for EDMM considers superheating of electrodes due to heat transfer from plasma. As we have seen in the last lecture, very high temperature is developed during EDM and EDMM process, that may be few thousands degrees centigrade. So, this is very important to consider. Melting and superheating is the main mechanism of erosion. Material removal takes place at the end of on time, and whatever material is melted out, it should be thrown out of the inter-electrode gap, and this is done by flushing of the dielectric. Now, however, the flushing pressure or the velocity of the dielectric flow in case of EDMM is not very high. So, something should be developed so that the electrode gap is cleaned and you can have better performance of the process. It considers strong electrostatic force acting on electrodes. Mechanism of erosion is yielding during the on time and material removed due to electrostatic force. Apart from the flow of the dielectric, this electrostatic force also helps in removal of the material from the gap. Modeling for temperature distribution in the workpiece, determination of crater volume formed by single spark and determination of material removal rate. Both of them are important because this crater formation will help you in the removal of the material, as well as it will also control the surface finish of the final component. Larger the size of the crater, or I mean deeper the size of the crater, rougher will be the surface, and shallower the size of the crater, finer will be the surface. Determination of thermal stresses in the workpiece, this is another important aspect, because minimal thermal stresses should be there, thermal residual stresses should be there in the machine component. Otherwise, it may fail during its use prior to its life or estimated life. Modeling for temperature distribution in the workpiece, there are certain assumptions, because whatever theoretical model you are developing, you have to make certain assumptions. The thing that one should take care of it or be cautious of it is the assumption should be as realistic as possible. Especially in the beginning, some assumptions are made which are not realistic, but later on they should be relaxed. The workpiece microdomain is considered as axisymmetric. The workpiece material is homogeneous and isotropic, which is in real life not true, but for theoretical analysis, yes, it is assumed. The material properties of the workpiece are temperature independent. This is another very important assumption, because most of the material, they are changing their thermal properties, mechanical properties and physical properties with change in temperature, but for theoretical analysis in this particular case, they are considered to be temperature independent. The heat transfer to the workpiece is by conduction and convection only. This simply means that heat transfer due to radiation is neglected, or that is not considered. Although temperature is very high, so substantial amount of radiation, heat radiation may be there, but for the analysis it is neglected. Now, this is the heat source. This is the Gaussian heat source which is being considered. As I told you earlier, many people have considered different types of the heat source. Some of them have considered uniformly distributed heat source. In this analysis, Gaussian heat source was considered. Governing equation. This is the governing equation which is used for developing this particular model. 1 over r del over del r multiplied by small k dt del t over del r plus del over del z, del T over del z is equal to rho C multiplied by del T over del T. This simply means that 2D it is being considered R as well as Z, where T is the temperature, small t is the time, rho is the density, and C, that is this capital C, is the specific heat capacity of workpiece material in solid state. As I have mentioned earlier in the assumption that the thermal properties are not changing with temperature, so this has to be kept in mind. And K is the thermal conductivity, and R and Z are coordinate axis. R coordinate axis is along radius, Z is in vertical direction. Boundary and initial condition. To solve such equations, you need the boundary conditions and you need the initial conditions also. So, you can see here del T over del N is equal to 0 on this surface, del T over del N is equal to 0 on this surface as well as on this surface. So, they are considered as heat is not conducted out from here or not convected out from here, or they are considered as insulated one. And here this is Hi T minus T0 in this particular case, and this is the Rs, that is the spark radius. R suffix x is the spark radius. So, when T is greater than 0, that means time is greater than 0, that means the process has started. Then you have this equation K small del T over del N is equal to Hc multiplied by T minus T0. If R, that is the radius, is greater than Rs, that is the spark radius, and this is equal to Qw if R is less than or equal to Rs. R means wherever you are evaluating the system on surface S1, and you can see here this is the surface S1. So, it has been divided into zones where where you are considering it is greater than Rs, that means beyond this value, and when this is less than or equal to Rs, that means this value, this zone. And del T over del N is equal to 0 on S2, S3, S4, and that I have already mentioned that they are considered to be insulated one, and Ti means initial temperature is equal to T0. So, this is Qw is the quantity of heat flux entering into the workpiece, that is over here. Rs I have already told to you, Hc is heat transfer coefficient, T0 is room temperature, and direction N is normal to the boundary, because N is being used here. Spark radius Rs plays very important role. It is found that electrode material influence the spark radius during EDMM process. I have already shown to you the curve proposed by Prem Shankar and others about the spark radius, and this spark radius is varying on the anode as well as on the cathode. They are different, and it is continuously varying in the inter-electrode gap, and it is minimal on the central plane. That curve I have shown to you, which was calculated theoretically on using this particular model. However, measurement of the spark radius is extremely difficult due to very high pulse frequencies. For a rectangular pulse, the spark radius Rs depends on time t, as in the following fashion. We have already seen the relationship between time and spark radius in the earlier slides. And Rs is equal to K, Q raised to power m, T raised to power n. Here Q is discharge power, m, n and k are empirical constants. These constants are defined in terms of the coefficients L, m and n determined experimentally for different electrode materials, because electrode materials may be different for different applications. K is equal to L capital over Lm plus 0.5 n, where m is equal to 0.5 n and n is equal to n capital N, and L is discharge length, and this you have to determine experimentally. The applications of the above expressions are limited, as they are valid only for few cases of selected electrode pairs and dielectric. That is very important. Heat flux due to, now before I proceed, because here certain constants are given and these constants are applicable only for selected electrode pairs and dielectrics. Heat flux due to a single spark. Most researchers have considered uniformly distributed heat source within a spark. This assumption is far from reality, as I have told you. Gaussian heat source is considered considerably. From the actual shape of a crater formed during EDM and EDMM, it is experimentally found that Gaussian heat flux distribution is closer to real heat flux distribution. QW function R, Q0 exponent minus 2 multiplied by small r divided by Rs raised to power 2. If it is assumed that total power of each pulse is to be used only by one spark, then the above equation can be written as follows. Please note it here, I have written one spark in the bold faces, mainly just to tell you that here single spark EDMM or EDM is being considered, but many researchers have proposed and found experimentally and otherwise also that there, if the conditions are prevailing, appropriate conditions are prevailing in the interelectrode gap, it is not single spark EDM or EDMM, it is multiple spark EDMM process also, but it depends upon the prevailing conditions of the tool surface and workpiece surface and the feed given to the tool. QWR is equal to RW VI over pi Rs square exponent raised to e raised to power minus 2 R by Rs square. Now, here you just substitute the value of Q0, you will get this particular equation, where V is the breakdown voltage or discharge voltage, I is the current, and Rw is energy partition to workpiece. In the last class we have already discussed that different researchers have given different partition energy in different cases, especially how much energy, percentage of energy is going to the tool, how much is going to the workpiece, how much is convected away, and this will determine, this partition energy will determine your all calculations. Energy partition in EDM and EDMM, the material properties of individual electrodes determine the fraction of input energy or input heat going into the electrodes. DiVincenzo et al. And Patel et al. Have used the value of Rw as 0.08, which is quite minimal, very small, for their theoretical work. But Shankar et al., they have calculated that about 40 to 50% of total heat input is absorbed by the workpiece, which is substantial. Now, which one is really correct will depend upon what you get theoretically and what you get experimentally. You can compare those results and determine which is more appropriate in which case, because both these models by Shankar et al. And DiVincenzo and Patel, they are based on certain assumptions, but even those assumptions may be different for different type of tool material, workpiece material, dielectric and so on. So, none of them is bad, none of them is good. You have to just check which one fits better in the given conditions. No comprehensive method has so far been proposed to calculate the value of RW during EDMM process. Now, actually whatever these 40%, 45% or 0.08, these are all experimental, or these are all based on experimental results, not on theoretical results. R&D is used in EDMM process. Micro EDM system development, because very few micro EDM systems are available in the market as well as in the R&D houses. So, lot of work can be done in this particular direction. Micro EDM process modeling, improvement and optimization, as I have shown to you in the earlier slides, that there are lot of scopes for theoretical modeling, lot of scope for simulated modeling, simulation modeling, just like you can apply finite element method, finite difference method, boundary element method, or GA and other kind of the techniques for simulation purposes, and lot of optimization work is also to be done yet in this particular case. More comprehensive theoretical modeling of micro EDM process are required for this purpose. Accurate control over the small interval, this is very important. Experimentally the devices should be developed so that they can accurately control the inter-electrode gap. This is being controlled by moving the tool towards the workpiece or away from the workpiece, because if it is not working well or flushing is not working well, then the cycle time keeps on increasing and material removal rate keeps on decreasing. So, the process becomes less efficient. Another thing is accurate control over the discharge energy is another aspect, where you have to control the voltage, breakdown voltage and other parameters, so that you input the appropriate and same energy to the machining, so that you get the repeatable results. Because if your discharge energy is varying in different discharges, then you may not get the repeatable results. So, this is very important and lot of work can be done in this direction also. Compensation of electrode wear, as you can see, hardly any good model is available for compensation of tool electrode wear for EDM and EDMM. So, you can do lot of research activities in this direction, because this will help you in designing the tools for EDM as well as EDMM processes, and if you can design the tool for EDM and EDMM processes, you will get the accurate repeatable results. So, research activities are needed in this particular direction as well. So, effective removal of debris from the small inter-electrode gap, proper flushing has to be done in case of EDM, and some appropriate methods have to be developed in case of EDMM process, because tools are of micron size. So, you cannot apply very large pressure on the dielectric, otherwise it may bend the tool, it may damage the tool. So, appropriate work has to be done in this direction, so that the reaction products and debris are removed from the inter-electrode gap quite fast. And in process measurement of part dimensions is another new area. If you can measure the part dimension on machine or in process, then you will be able to control the process in a better way, and better dimensions and accuracy will be obtained for the machine component. Concluding remarks. As we have seen in the last two lectures, micro EDM and EDMM has a great potential for micro machining, because nowadays in all fields of life miniaturization is taking place, and if miniaturization is taking place, you need the micro components for making the miniaturized devices, and so this has lot of application, although it has its own limitations also, because it is a thermal process. The process has been extensively applied to generate microscopic features. I have shown you the examples of various micro features that have been successfully developed using this EDMM process by performing different types of the operations. One of the important requirements of the micro EDM is the availability of an electrode of desired shape and size. I have already told you that how to develop or how to fabricate the micro electrode by different methods using either micro EDM process or micro ECM process. In this regard, there are a number of methods available for fabrication of the required electrodes by different techniques. It may be noted that the scale of micro EDM process is closer to a single spark of the EDM process. I have already told you there is a different opinion of the different researchers in this direction as long as single spark is concerned. However, multiple sparks are also there in certain processes under certain conditions, but theoretical work is almost negligible as long as multiple spark EDM and EDMM are concerned. It may be possible to extrapolate finding of single spark phenomena to multi spark phenomena in micro EDM. So, that possibility has to be explored by the researchers before really it can be implemented on the shop floor. For better understanding and control over the micro EDM process, more efforts are needed towards its theoretical modeling. With this, I thank you very much for listening it. Thank you.